Hi everybody, my name is Alex Robey. I'm an engineering math double major, and I work in a field called computational optics. And today I want to talk about microscopes. So microscopes are great because they let us take pictures of really small things, right? But sometimes we find that we can't get enough resolution out of a microscope. So it turns out that all microscopes are inherently limited in the achievable resolution by the quality of their lenses. So that means that I might have a really good microscope, but the lens still isn't quite good enough to get the amount of resolution out of it that I might want. And this is a problem. Luckily, there's also a really good solution, and it's called Fourier Pytchographic microscopy, or FPM for short. So this technique actually has a really simple idea, and that's that if we take a bunch of pictures of the same sample, maybe that's something like a cell, and we stitch them together in what's called Fourier space, then we can actually reproduce a super resolution image that has a much higher resolution than what we would have ordinarily been able to get out of a regular microscope. And this is great because now we can take pictures of things in super high resolution that we just wouldn't have been able to get without this technique. Now, there is one caveat, unfortunately, and that's that in order to perform this technique, we need maybe around 1,000 or 10,000 images to stitch together. And that's just computationally infeasible. It takes too much computational time to stitch together that many images. The way we take these images that we stitch together is we illuminate them from underneath with an LED array, which you can see at the bottom of the slide there. Each illumination pattern corresponds to a different low-resolution image that we would want to stitch together into a high-resolution image. And so we just don't have time to take 10,000 individual images. So my project for the last 2 semesters has been to think of a way that we can more effectively perform this technique without resorting to stitching together thousands and thousands of images. And what I've done is I've used something called machine learning or machine intelligence to find a way to speed up this process. So what we're looking for is the optimal or several optimal LED patterns that will illuminate a sample from underneath to reproduce the same high-resolution images that we could get from stitching together 10,000 images. And it turns out that we've been very successful with this. So we've actually found an algorithm that looks at all the patterns and all the low-resolution images and can tell us the very best illumination patterns to reconstruct a high-resolution image. And here on my slide on the right here, you can see one of those images. So the dark purple corresponds to LEDs that are turned off, and as the colors get brighter, that corresponds to LEDs that are on. And what you might notice, and it may be sort of surprising, is that it's kind of an asymmetric pattern. Maybe you'd expect all the LEDs would be turned on, and that would be the best illumination pattern to most effectively reconstruct a high-resolution image. But it turns out it's not the case, and this surprised me. Maybe this goes against my intuition, maybe all the theory that I could have would point to a different conclusion, but in the end, I just found that I have to pay attention to what the machines are telling me and give over control to what machine learning says. Thank you.